Although this will be the marathon for our chemistry syllabus full final term, and so let's just begin. We'll go for the harder topics and work our way to the easier ones, starting with acids, bases, and salts. So acids, bases, and salts. Right, so what are acids, bases, and salts? Acids is any substance that produces H plus ions, alright? It produces H plus ions, and in an aqueous solution. Very important. You must mention that it does this in an aqueous solution, or else marks will be deducted. And okay, yeah, that's pretty much it for the definition for acids. The rest we'll touch later. Let's talk about strong acids and weak acids now, because we need to know a few properties of acids. Now, an important thing: do not mistake concentration and strength of acids. A concentrated acid or a dilute acid does not mean it's strong or weak. It's just the amount of water that is in that solution with the acid, alright? Where if water is of larger amount than the acid, then we call it dilute, right? We call it dilute. But if it's the other way around, where the acid's amount is more than the water or any other substance, we call it concentrated. Concentrated. Now, let's talk about strong and weak acids. So what are strong and weak acids? I have a few points here. So strong acids are fully ionized in an aqueous solution. Remember, again, please mention aqueous solution or marks will be deducted. Weak acids are partially ionized. I wrote half because I'm too lazy, but remember, please write partially ionized. Do not write half ionized. That's wrong. Write partially ionized in an aqueous solution once more. And then the next point is they fully dissociate. If that's hard to remember, you can also write that they are of lower pH than weak acids. And weak acids are of higher pH than strong acids, but less than 7. So that's neutral. And anything above 7 is considered an alkali. And then you can give some examples. You can give any example you want. You can the example you can give for strong acid could be anything like HCl, H2SO4, hydrochloric acid, and sulfuric acid, your choice. And from weak acid, you can give something like ethanoic acid, anything like that. Citric acid also works for strong acids. Right. That's the strength of acids gone. We can now talk about various sort of equations. We have what's acids plus alkali, acid plus alkali. Then we have acid plus metal. We have acid plus base, but that's the same as acid plus alkali, so we don't have to worry about anything. Right, there's also acids plus carbonates. Okay, these have different products. Acid plus metal gives a salt plus H2 gas. Acid plus carbonate gives a salt plus CO2 gas plus H2O. I can double check this. I'm not 100% sure, but I'm pretty sure it's this. As for acid plus alkali, it's just salt plus water. Salt plus water. Right. Now that we're done with this, keep these in mind. Alright. Now we go into the next topic, just the next part of this chapter, which is about alkalis. Before we start alkalis, we need to know what is a base. What is a base? What is this weird shit called a base? Well, a base, in general, is just any metal, oxide, or hydroxide. Okay? Is any metal or oxide or hydroxide which, when reacting with an acid, produces, as we already know, which is, what is it? It's water plus salt. Actually, salt plus water. Why did I put it that way? Salt plus water. Right. Now we know that. Now we can go into the next part, which is an alkali. And a very important thing I almost forgot. A base is insoluble. All right. Remember, bases are most bases are insoluble. I'm saying most bases because the other half that is soluble is an alkali. So what is an alkali? An alkali is a base. Okay, so you can say in general that all bases are alkali, but not all alkali are bases. That's because an alkali is a base which does dissolve. All right, alkalis do dissolve in an aqueous solution, or does dissolve in water or aqueous solution, whatever you give. So bases that are in, or not in, that are soluble. Basically, a soluble base, which gives the same products as the original base we have given. But the important part is that they produce OH minus ions, which, by the way, bases don't produce because they're insoluble. Okay? Right. Now that we're done with this, bases, alkalis, basic stuff, we can move on to the next part of the topic, which is about indicators. We have universal indicators and a few non-universal ones. Basically, just other types of indicators. The universal indicator is that red litmus means it's an acid or is acidic. If it's blue litmus, in that case, it is alkaline. Another important thing to keep in mind, it's only for universal indicator. The neutral is green, okay? So for neutral, it's green. That is if it's neutral. Okay, there is no extra part. It's only if it's neutral. Right. Now, let's talk about a few of the other types of indicators we have. We have one called methyl orange, I believe we got this in our second subject test. And methyl orange in an acid gives out pink. So acid, it is pink. And in an alkali, let's say, in an alkali, it is yellow. Right? A few other ones you want to keep in mind. Another one is called thymophthalin. I might be wrong. Thymophthalin, which basically in an acid is no color, so it's colorless. And in an alkali, it is blue. So in an alkali, it is blue. Right. Right, that's all for the more important ones of universal indicators. There's no really need for the other ones. Now comes the next topic we're going to talk about. This next topic we're going to talk about is going to be about oxides, the different types of oxides. And once we're done with oxides, we're going to start about neutralization reaction. So what are oxides? Well, there are different types of oxides. We have acidic oxides. So an acidic oxide is a non-metal oxide, right? So it is non-metal. So we have a few bullet points. So it's non-metal. It's a non-metallic oxide. So it's a non-metallic oxide, right? So a non-metallic oxide, and it has some acidic properties. You can say it has a few acidic properties going on for it. That's all you gotta know, okay? It's a non-metal oxide. That's like the main gist you have to remember, right? Because anything else is not that big of a deal, but it's important if you know this one part over here. Right. So going on for the next oxide, which is called basic oxides. So what is a basic oxide? A basic oxide, or another name for this oxide, is called metallic oxides. That is weird and right. This is happening with a bit of a delay. My computer hates OBS. So it's metallic oxide. Okay? A metallic oxide. That's basically what a basic oxide is. It's any metal oxide. Then we have something that's very important. Amphoteric oxides. I might be wrong with the spelling, so amphoteric oxides. So amphoteric oxides are oxides that react with both acid and alkali. Alright? This is very important. If you want to know which oxides these are, because they are very, very important to know which one they are, you can memorize it with this little small issues. I call it ZAL, which stands for zinc, aluminium, and lead. Well, specifically lead 2. Hopefully you memorize that. Lead 2. Zinc oxide, aluminum oxide, lead 2 oxide. All of these are amphoteric oxides, meaning they react with both acid and an alkali. Right, that's for oxides. Now let's talk about classification of salts. Now I'm pretty sure this is very obvious and you should know these very well. Firstly, we have something called the SPA, which basically means any sodium, potassium, and aluminium salts are soluble, right? All chlorides are soluble except for lead 2, and silver, right? As for fluoride, that's chloride, then we have sulfates. All sulfates are soluble. Okay, all sulfates are soluble except for, okay, let me give some crosses. These two do not, right, except for barium sulfate, okay, then we have barium, calcium. Right, so we have barium, calcium, and wait, hold on, let me remember this. This one is very hard to remember. Okay, barium, calcium, and lead 2. So lead has a bit of a trend with not being easily dissolvable. But you know what is easily dissolvable? Nitrates, NO3s. Is very magical because all nitrates are soluble. There's no exceptions for this one. Then we have hydroxides and carbonates. All of them are insoluble except for our SPA, which are, you guessed it, all soluble. So SPA, everything is soluble. Nice. That's for that. Now we're done with classification of salts, we can now move on to the next part of our topic. And the next part, I think that's pretty much all for acid bases and salts. Did I miss anything? I might miss, oh yeah, preparation of salts. Who can forget? Preparation of salts, right. Preparations of salts. Preparation of salts. Preparation of salts, right. So what is preparation of salts? Preparation of salts, there's 3 methods. There's method 1, there's method 2, and there's also method 3. So method 1, and method 2, method 3, okay, let's write these down. So we first have method 1. Method 1, we use method 1, which is basically acid plus metal. And here, let's say we want to prepare a magnesium chloride salt. Alright? And magnesium chloride is soluble in water, so we must do acid plus metal, right? So you can do acid plus metal. But for that, if we want to do any of this, This method can be only used for a specific group called the Mazet group. Alright, it stands for magnesium, aluminium, zinc, iron, and tin. These are the only ones that we can use this method 1 for. So with magnesium, we add HCl, right? We add HCl, and then we get our stuff. So what is the full procedure? The full procedure is in a beaker. We fill it half the beaker with dilute hydrochloric acid. Then we add excess magnesium, and then we then filter it, and we collect the filtrate. If it says to keep it as a solution, then this is all we need to do. If it says to take solid crystals, then we also add the crystallization process. We'll talk about that in a bit later, because we got a few more chapters before that. Right, crystallization. So that's later. So that's pretty much it for method 1, right? And a question might come is, why are we adding excess magnesium to this solution? It's because excess magnesium is given so that it uses up all of the acid. Okay? Okay. The method 2 is tritation, and I have a little process of tritation. I had it, but I don't have it now. But basically, tritation, you already know what that is. If you do not know, I will link a PDF file which is given in our Google Classroom. I don't know whether it's given for other sections. Section C has received this little bit of a little note thing in our Google Classroom, and from this section C, I'll give you guys the note, no problem. You can check out tritation from there, as well as every other acid bases and salts part. Okay, that's for acid bases and salts. We can now finally move on to the more, you can say, a little more simpler topic. Okay, acid bases and salts is a pretty annoying topic to work with. Right, the next topic in our syllabus I want to talk about is called the periodic table. And it's basically what's going on in each group, how each group works, and what so on and so forth. So this is a very small chapter, very simple to understand. I'll just tell you the more important ones. You gotta know what trends happen as you go lower down the groups. All right. Right. Remember this: the groups 1, 2, 3. I can put up my periodic table. I should double check actually. Let me bring up my periodic table. Yeah, groups 1 to 3, the lower you go, alright, the more reactive they get. The more reactive they get, the lower you go. But, on the other hand, from groups 4 and beyond, not 4 to, from 4 to 7, the higher you go, the more reactive they get. The lower you go, the less reactive you get. The reason is because 1 to 3, they give away electrons. We should know this from the ionic bonds chapter, which we'll also touch later on after this. And how this works is, the lower you go, another important thing is that the atoms get bigger. They get more and more bigger as you go down the group, right? And because they get bigger, their distance increases between the nuclei and the outer shell electrons. So it's easier for them to lose said electrons, and in turn, they easily give away, which means the bigger they are, the easily they give away, and hence they're more reactive. But on the other hand, the job of a nonmetal is to gain electrons, meaning they need to be as small as possible to have the best forces of attraction, meaning the lower you go, the bigger they get, which makes the job harder because the force of attraction gets weaker. So that's why the higher you go, the more reactive it is. Group 8 is special because everything there is unreactive. No reactions take place because they are inert, meaning they have a full outer shell of electrons, which is neat, I guess. They don't have to worry about any sort of reactions. Another important thing you must know is the uses of these inert gases. Helium is used for hot air balloons. We got neon is used in signs, you can say. And as for tungsten, not tungsten, what am I saying? And argon is used in tungsten bulbs as the filament to create an inert atmosphere. That's pretty much it. And group 1, by the way, are called alkali metals, and that's because they have little, like, small little properties of alkali, which is a fun little thing. And group 1 to 3 are good conductors of electricity. They are good conductors of electricity, and they form minus ions, alright? They form minus ions. You need to know that. They form minus ions. Right. That's pretty much it for periodic tables, actually. There's also displacement reactions, and how displacement reactions work is, say we have a sort of compound, okay? And you add another element to this compound, it can replace what was there originally because it is more reactive. I think we should give an example, or else this would make absolutely no sense to you guys. Right. Let's bring out a periodic table, and maybe we should see them there. This only occurs with halogens, I think. I'm not really sure. Yeah, it only occurs with halogens. So let's say we have something like potassium iodide, right? And we add bromine. It will be potassium bromide, and that's because bromine is more reactive than iodine. So a little fun way you can think of this is, let's say this iodine is like a teacher, this bromine is like a principal, and he's like, I can remove you if I want to, and so he removes this iodine, and it goes away, and now it's with the potassium because the iodine is too weak to do anything about it, obviously, because it is slightly less reactive. Right, that's pretty much it for periodic table. It might sound crazy, but we are done with 2 chapters already. We're zooming through, right? We're going through most of the chapters. The next chapter we have, alright, this one is going to be another long one, is ionic equations. Not ionic equations, any equation building in general. You need to memorize, unfortunately, a bunch of shit from here. I know you hate memorization, but you really got no real choice. The main memorizations are of the group metals, not like the higher group metals, you know, the charges, because we don't know what the charge is usually, and most importantly, the transition metals. And speaking of which, I think I missed transition metals from my periodic table chapter. Let me double check. And yep, I definitely missed it. Yep. Alright. My bad. There's still one more extra part. That is the transition metals. So transition metals, all you need to know is the properties, which are they're less reactive than group 1 and 2. Alright? They're less reactive. But there's a catch. They are stronger. Right? They are strong. They're very strong. That's a bad looking muscle. They're also harder. Okay, they're more harder in general, and they have high density, right? They have high density. So that's pretty much it. They also act as a catalyst, but that's not really that important. Another important thing is uses of these transition metals. Is that we can say like copper is used in electrical wires, monos like an alloy of copper and nickel, and alloy of stainless steel, and all that whatnot. So yeah, you should know that. There's also like the position of hydrogen, but that really doesn't matter. It's just that hydrogen has like mixed properties of both inert gas, which is like group 8 noble gases. Not noble gas, what I'm saying. It just has a lot of mixes between halogens and like it had like a halogen and like group 1, because for some reason it can produce both a negative or a positive ion, so it's like an exception. That's basically that for the position of hydrogen. Now, let's talk about the next topic, finally. We're going to talk about equation building. This one is going to be the trickiest one for most, but I'll teach you a few tricks and tips and tricks and stuff. We should start with a few things, which is memorizing a few tables, unfortunately, which is the charge tables. Okay, a little trick you can learn. Let me bring out the charge table actually in front of me so that I can tell you what it is going to be. Let me go through my notes. Writing chemical equations. Alright, now this chemical equation writing can go from small chemical equations to like larger ones. Basically, it's all down to balancing and stuff. I don't think I have a balancing. I have a balancing whiteboard too. I can show it to you. Let me go to the balancing whiteboard real quick. I have to look for it. Hold on. I don't remember which one it was. I think it was this one. Okay, let me go through my balancing whiteboard. I have done all the balancing equations, and I'll teach you a little bit of a trick to do these balance equations. Because they're not that hard, they seem hard, it's just because people just over exaggerate how they are. So let me just wait for this to load. Just go in. Alright, so here is the balance equation. So let's begin. So start with here. Let's see what's going on here. We have 3 hydrogen here, we have 2 hydrogen here, we have 2 nitrogen here. Well, here's the thing, there's 1 nitrogen here. Let's say we add a nitrogen here, right? Now this nitrogen is balanced out, but this hydrogen is even more unbalanced. We have 6 here. To create 6 in here, we just add a 3, and there you go. We have 6 here, it's balanced. Nice. Let's go for the next one. Alright, this one, there's O2, there's 2 oxygens. There's 3 oxygens here, there's 2 here. Alright, let's see, is there any other extra things? Nope, it's just the oxygens. So we can do something. Let's say we can make this oxygen 3, we make this 6, we make this 6 as well. What are we left with? We have 2 potassium, 2 chlorine, we can just add a 2 in here, and there you go. That's also solved. Let's zoom a little more actually, so it's easier for me to write. So much better. Now, NaCl, F2, NaF, alright, all this. Let's see, there's 2 fluorines here, so we can add a 2 here. So that's done. There's 2 sodiums, so we can add 2 here too. And whoa, magically, the chlorines also just work out, and you're done. Alright, H2O. Okay, this one looks like a tricky one, you might think, but it's not that tricky. Let's add a 2 here. There's 2 oxygen, 2 oxygen. Nice, that's balanced. There's 4 hydrogen. That's the problem. Let's add a 2 here. Now there's 4 hydrogen. Nice. Okay, now I got something that's more interesting. If there's a bracket, this 2 is being multiplied with both the hydrogen and the oxygen, not just the hydrogen, right? So in total, there are actually 3 hydrogen here. There's 2 here and there's 1 here, right? And on this side, we have 2 hydrogen only. So if I make 3 hydrogen, I think we should see if there's any other extra stuff, right? First, I see there's 2 chlorine. So let's add a 2 here. Okay. So in total, we now have a different number. We have 4 hydrogen. We can add a 2 here. So there's 4 hydrogen. And look at that. The oxygens also balance out. There's 2 oxygen here. There's 2 oxygen here. And we're done. Okay, I should reduce the thickness of my pen, actually. It's too thick for me. Oh, it's much better, right? Allo, okay, we have Al, Br3, all that weird stuff. So there's 2 aluminiums here, so let's add 2 here. Let's add 2 here. There we go. Okay, Br, bromine, whatever, there's 6 here, so we can add a 6 here. Okay, there's 6 bromine. Alright, so from here we can see that there is around how many amounts of oxygen? There are 12 oxygen. To get 12 oxygen here, we need 3. And to look at that, if I give a 3 here, this becomes 6. And that's 6. This becomes 3. And you can see this 3 becomes 3, this becomes 12. This becomes 12. There's 2 aluminium, and this is 1. It's balanced. Now, C, there's CH4. That means there's carbon here. So 1 carbon here, 1 carbon here, nothing to do. 2 oxygen, nothing to do. 4 hydrogen. Oh, actually, no, there's 3 oxygen. There's 2 oxygen. Alright. Any other extra stuff? Okay, the hydrogen. The hydrogen feels more easier to do. We can add a 2 here. The hydrogen is now 4. But there's a total of now 4 oxygen. So we can also add a 2 here, and now we have 4 oxygen. Basically, isolate it. Isolate your elements, and then you can do the job. Now, let's go for the next part, which is CH3, H8, O2. Alright, you already know what to do. And in turn, you just start using this method where you basically single out one specific element, work on that element, and somehow automatically everything just starts to fall in place. And also, if you ever have a situation where you're feeling a bit zesty and you use fractional balancing, I'm pretty sure you're not going to do it, but if you do, what you can do is, if you have a lot of fractions, take the LCM of the denominators and just multiply it, and it'll be automatically balanced. So that's basically that for chemical balancing. Let's talk about ionic equations, right? What is an ionic equation? Let's give an example of an ionic equation, shall we? a lot of ionic equations we give. Let's see. Alright, this one looks nice. Alright, so we have one here, let's say Na2 CO3 plus H2SO4. This is equals to, actually arrow, NaSO4 plus CO2 plus H2O. Alright, an important thing, there's AQ here, there's also AQ here, there's also an AQ here. This one is a gas, this one is a liquid. Now, I think you should know a little trick for you guys. Since you're not supposed to show this rough, where you break it down and stuff, that's for your understanding. If you want, since they want the answer to be direct. Now, another thing you want to know is that usually, another thing you want to know is you gotta balance this beforehand. So this is just 2 sodium, so let's add a 2 here. Right, the amount of sulfur becomes 2 as well. Right, there's just 2H there. Alright, CO2. There's how many oxygens are here? There are 3. Right, this is 3. This is 4 oxygen. There's 4 oxygen. Nice. Okay, I added 2. There's not 2 NAs. Oh wait, I missed something. I think. Oh, I missed something. There's a slight mistake. That's what I thought. Na2. So 4. Now it's right. Okay, there's no balancing to be done. If there is balancing to be done, you do the balancing beforehand. A little trick you can use is see what's aqueous, and in your rough, cut this. Cut this. You're not supposed to show the rough work, by the way. I know it feels weird, but you're not supposed to show it. SO4 are similar. SO4 gets removed. Anything else? No. We're left with this. So you answered with CO3. I'm gonna give the charge for carbonate plus, I'm gonna give H2. The charge for H2 is equals to CO2 plus H2O. You have to state symbols. This one is both going to be a Q. This one is also going to be a Q. This one is just a gas, and this one is a liquid. Alright. Now, this charge, the charge for carbonate is minus 2. No, actually, it's minus 1, I believe. Wait a minute. I can't remember the charge for carbonate. This is very stupid, but the charge for hydrogen is, of course, plus 1. Sure, plus. And you have to charge for carbonate, and that's basically all you have to do. Okay, let me double check. Yeah, okay, it's minus 2. It's minus 2. Yeah, that's right. So this is the answer for ionic equations. Basically, you break it down, or the shortcut is take what's AQ. If it's similar, cut. What you're left with, just write it down with the charge, and you're done. That is just what ionic equations are. And normal chemical equations are just this part. Like you just make this without doing any ionic part. So that's all for chemical equations. Now we're done with that. We'll finally move on to the next chapter. Alright. We are soaring through this. The next chapter we have left. Alright, we're done with that. Right. I think that's for the final term. We're done. Oh yeah, we got apparatus and stuff. Oh boy. Apparatuses. So what are apparatus? It's part of the chapter 14. There's 14.1 and there's the 14.2. So let's start with 14.1 because it's all connected. 14.1, we talk about different types of apparatus. So since we don't have time, the main thing you need to know is that a burette is the most accurate, or I can't draw a burette, but you get the point. A burette, you can say, is the most accurate. So if it mentions burette in any way, it's the most accurate. So a burette is most accurate. Then there's a pipette. A pipette looks something like this. It is for like a fixed mass or fixed volume of a substance. There's also a measuring cylinder that is, well, not that accurate. So, if you're given a question where you say a student wants to accurately measure a substance, you use Biret. If it says a student wants to measure this quickly, then you use a cylinder because it's faster. Remember this, the accuracy of a Biret is up to 0.01 and it increments by 0.1. Basically, it's like 0.1 plus minus. For measuring cylinder, it is a little more than that, where it increments by 1 plus minus. No, it increments by 2 actually, my bad. It increments by 2, and it has an accuracy of 1. So that's that, and that's basically the more important ones. The pipette is for a fixed volume, where you only want exactly 25, let's say 25 mm³ of a substance, and use the 25 mm pipette. Right, so now we talk about, I think that's that for that, yeah, alright. Now we talk about extraction of gases. Right, so let's say a gas, we have a gas, alright, and it is denser than air. If it's denser than air, that means we have to use downward delivery. And a very important thing is that if this is soluble, meaning it dissolves in water, if it dissolves in water, that means we use downward delivery. If it is not soluble in water, for any case, whether it's less dense or more dense than air, we would immediately use the displacement method. If it's soluble in water and is more dense than air, we use downward delivery. If it's less dense than air, we use upward delivery. Okay, that's that. There is now drying of gases. Drying of gases, we have using like dilute sulfuric acid. I think that's the first one. Not dilute. I think it's concentrated. Let me double check to be absolutely sure. Because basically using sulfuric acid, that's like the main gist you have to know. Double check my notes because I don't want you guys to fail. That is not what my job is. No, we have to use concentrated, right? So if you use concentrated sulfuric acid, H2SO4, and this is for the extraction of most gases, right? Except for ammonia. Except for ammonia. For that, we use quicklime. Quicklime, you use quicklime. And to find hydrogen, we use fused calcium chloride. Right? To get dry hydrogen gas, we use what's called fused calcium chloride. Right, that's all for this. Now we got the second part, which is 14.2. This one's a little more interesting, because this details about the next part of the chapter, which is about the various ways we can extract things, alright? We gotta start with filtration. Filtration is basically we have two, we have one insoluble, one soluble. We add a solution or a soluble, whatever, to make it dissolve with that thing, and basically filter it out. You know what filtering is, right? I'm sure you see your mom make tea, and you see her put the tea together and like filter it out. That's basically what filtration is. Yeah, okay. Then there's distillation. Distillation, how it works, it separates um, a, a solute from a liquid, right? No, it separates something that is, I believe, insoluble or soluble. I don't think. Um, oh yeah, you're supposed to use this to separate a pure solvent from a solution. All right. So how can this be done? Is we first heat the flask. This makes the water vaporize up, condense into water again, and be collected in a beaker where it separates two liquids. There's also fractional distillation where there's glass beads here. This is for the separation of not gases, liquids, and two liquids, two liquids, gases, where basically the one with the lower boiling point rises up, and if the other one also rises up, then it condenses in the large surface areas of the glass beads and falls down, while the one that is supposed to go just goes in and gets collected. Right, now there is also, if there's two insoluble um, stuff like oil and water, we use what's called a separator, which separates the two. It's not that important. Separating funnel is not that important, but just for you to keep in mind, of course. What is important is crystallization. Crystallization. This is the most important one. Let's say we want to obtain pure copper, copper 2 sulfate crystals. So what is the first thing we want to do? The first thing we want to do is if it's impure. Okay, it's only for if it's impure. We want to first filter it out to remove all the insoluble impurities. All right. Right. If it's pure, then we directly put it into a round bottom beaker or round bottom flask, whatever you want to call it. But the main thing is we heat this solution until it is saturated. All right. Until it's saturated, and once it's saturated, it's left to cool. And when it's left to cool, it forms these sort of crystals. All right. We then we filter to collect the crystals, where we wash them with cold distilled water. So we wash those crystals. So we wash them with cold distilled water. Wash these crystals, and then we dry them between sheets of filter paper, and that's basically what crystallization is. Remember when I talked about it in bases and salts about using it in a specific method? This is what I meant by adding the crystallization method in the end, when we want to get that pure crystal at the end. Right, that's that. I think all we have left is chromatography. Chromatography, alright, since we don't have time again, I'm going to only tell you the most important ones. Is that there's an RF value, we'll talk about that later, but the main thing I want to know is, say we have chromatograph paper, this baseline is drawn with a pencil. It's because if it's drawn with a pen, this is the way you write it. The reason why is because the pencil cannot be separated by the solvent. It's not separate or gets separated by the solvent. Right? Do not write dissolves. For some reason it's wrong. I don't know why, but if you write does not separate from solvent, it's right. That's why we use a pencil and not a pen, because a pen separates when it's dissolved in a solvent. Okay, the next thing. The dots must be above this baseline, by the way. Not above, sorry. The dots and the baseline must be above the solvent. Alright, the solvent travels up, creating these small dyes. The main thing you must know is that when you're finding the RF value, which is basically the solvent's distance traveled by whatever, or what I like to call it is the big number divided by the small number, the small distance between the dot divided by the distance up to where that solvent went. So, what you want to know is that when we count, we take the baseline at 0 centimeters. We count from the baseline upwards. All right, we want to count from this baseline, and we count it up to the dot. That will be the, let's we count to this dot. That will be on top, and then we take from the baseline again all the way up to where the longer line, which is up to where the solvent traveled, we divide it by that line, and we get our so-called RF value. And that's basically it for 14.1 and 14.2. Now we can go on to the revision chapters. We're done with the final term syllabus. Not final term syllabus, the ones that we are taught in finals. Now we'll touch ionic compounds and ions and stuff. Periodic table wasn't so hard, but who cares? Anyways, I just talked about it. So, ionic compounds. So, what is an ionic compound? The main things you want to know is that they are malleable. So, they are malleable. Oh, wow, I'm having a bit of a stroke with my writing. Malleable. Malleable. Can conduct electricity. Okay, they can conduct electricity. Malleable. Can conduct electricity. They are ductile. And, okay, that's pretty much it. Oh, and remember when I said they conduct electricity? That's only in a molten state. And that's because in a molten state, they have free moving ions, alright? And it's a really important thing. Ionic compounds can produce electricity because they have free moving ions. So not to be confused with a metal. A metal can conduct electricity because it has free moving electrons, not ions. That's different. Alright? Good. Now why are they malleable? That's because the ions can slide over each other. Okay? Right. Let's go to the next part, which is metallic bonding. Metallic bonding is the bonding between positive ions, so I can write positive ions, and negative delocalized electrons, or the free moving electrons, whatever you call it. It's the bonding between them. And if we're ever given to do a metallic bonding diagram, it is like the one where you give the elements in like circles here, and then you write E minus, E minus, E minus, E minus. And when you're given to describe the diagram, the 2 points you have to write is that C of delocalized electrons, so they're in a C of delocalized delocalized electrons, and that these ions are closely packed. Okay. Right. So that's that. Now we go to covalent bonding. And I think you know what covalent bonding is. What we want to know is the properties of a few specific covalent bonds, which is called giant covalent structures, which are diamond, and because my whiteboard is a bit tweaky, I'm just going to recite this. Diamond, graphite, and sand. You want to know why they have high melting points, and they have a high melting point. That's because they're a giant covalent structure, alright? That they have a repeating tetrahedral shape, and because of this, they have a high melting point. And we can also write that in diamond, one carbon atom is bonded with 4 carbon atoms. For lead, 1 carbon atom is bonded with 3 carbon atoms, and for silicon dioxide or sand, it's 1 silicon bonded with 4 oxygen and 1 oxygen bonded with 2 silicon. Okay, good. Now, that's that. And an important thing is that only graphite can conduct electricity because it has free moving electrons. The layers of graphite can slide over each other, and that's because the graphite is slippery, okay, because the layers can slide over each other, right? That's covalent bonding. And I think that should be all for the syllabus. And you might think, wow, I just gave up at the last moment, but dude, my whiteboard is tweaking. I really don't know whether the rest of this lesson went on 2 frames per second when I was writing stuff. Whatever, let's just hope my voice is okay. So that's pretty much it. I don't think I missed any stuff. Let me go through acid-base salts. That's the bonding structure. Did I miss anything from this chapter? Metallic bonding structures. Nope. Oh yeah. Dot cross diagrams are important, but you should know what that is. That's from plus. That's grade 7, so that should be easy. Alright, so that's it for today's lesson. See you later, and I hope you get an A star.